Yeah, okay. Hello, everyone. Welcome back to our seminar. So it's my great pleasure to introduce our today's speaker, Leonard Poker. He is currently a PhD student at the University of Freiburg, working on tabular data or machine learning for tabular data. He's also one of the core contributors to AutoGluon. And yeah, I'm pretty excited about today's talk. So he's going to present TabArena, which is um, a large benchmarking suite for machine learning methods on tabular data. And with that, thanks for joining us, Leonard, and take it from
Yeah,
here.
thank you for having me. Yeah, nice to finally be able to contribute to the AutoML seminar, also myself. So the P part is, as Aaron correctly said, this is about benchmarking, which might sometimes be very boring, but the important key aspect is that we are talking about a living benchmark. And to motivate a little bit why we need a living benchmark, I will start with a bit of a motivation. And the first one, for example, is unreliable baselines. So what happened a lot in previous work is that there was a benchmark and then they shared, for example, pre-computed results, and you get a table like this where you can compute essentially the average rank of certain models and then compare them, for example, to your model. And then you would develop a new method and try to figure out how can you get a score that is better or a model that is better on average rank than XGBoost. And we also looked at this pre-computed data of one specific data set, benchmark here. And we were like, okay, what happens if we just take the models in this benchmark and rerun them again with, like, say, the same pipeline, but some minor fixes, right? And we immediately noticed that if we do this, suddenly our models already get better. And specifically, for example, this MLP, which previously was pretty bad, got also somewhat competitive. And we even thought like one step further, well, okay, the evaluation protocol of this benchmark uses holdout validation. We don't really think that's a good idea. Let's use something different, like five-fold cross-validation, but still the same pipeline. And we also ran that. And if you now look at the results, you suddenly have this method which has a really, really good average rank, completely outperforms the baselines. And if you would, like, for example, submitted a method that is just a tuned XGBoost to NeurIPS or ICML, you might have gotten a paper accepted based on these results. And that's a bit of the problem, right? These baselines are unreliable and we don't really have a good guidance for which one should use for writing a paper or for benchmarking in general. So that's one big problem, the modeling space. Another motivation is insufficient dataset curation. So what was a very common tendency in the past with some minor exceptions is that people just assume that if a dataset is online available somewhere, it must be in a good state. So we just get all datasets we can get from internet, download them, benchmark on them, and that will be really, really good. And here, for example, is a very good counterexample for this. It's the New York City taxi dataset, where you, for example, can see two versions, which we call leak and resolved. And actually, by default, if you just download the dataset, there is actually, I think, a feature in there which leaks the target. So the dataset is essentially mal-configured. And if you now run models on this, it actually is quite meaningless because they're just trying to learn this target leak. If we remove this target, so we resolve this problem, suddenly you have very different scores, right? Much, much worse scores. And importantly, the model rankings are completely different, right? So this is quite important because we found many datasets with such leaks in this specific paper. And for example, other authors did as well before. And this has a major impact later on your aggregated statistics and how you rank these models compared to each other. And here you can also see that, for example, LightGBM, the best model previously, was a tree-based model, and suddenly tree-based models are much worse once we resolve the leak because they might have been able to better exploit this leak. Besides models and dataset curation, also how you actually evaluate or how you set up your evaluation protocol is extremely important. And there's this great study, TabRed, which analyzes essentially what happens if you go to non-IAD data or data where you essentially need time-based splits for tabular data. And they essentially also looked at previous studies, and they found that there were many datasets in there that actually needed them and really needed them and should have been evaluated with these splits, but they weren't, and people just didn't care about it or weren't aware of it. And it's important that this is a difference because if you now compare here the top benchmark with normal splits and the bottom benchmark uses time-aware splits, you actually get different conclusions, right? And that's quite important because you want to figure out what method works for the data you're actually interested in. And if you're not using the data correctly, then your conclusions are biased. And these three key problems that I've just shown you are essentially just one of many that always pops up once a new benchmark is discovered or once we make progress in this field. So what has happened then in the past is that essentially people have been developing every time a new benchmark that either completely changes the protocol or does something completely new, fixes some minor problems, but creates other problems. And the solution that you could now think TabArena is that we just do one more benchmark and that should fix it. We need just another lane and our traffic problems will be solved. And essentially, with TabArena, we're proposing that that's exactly not what you want to do. That's the wrong way to do it. Instead, we need to have benchmarks that can actually be updated continuously, right? Like a software version update, that if we find a problem, we can just solve this problem and all have like a much better version afterwards. And the solution that we then essentially propose that we indeed need a new benchmark, but this needs to be a living benchmark, such that TabArena, so this living benchmark, really aims to end any kind of malpractice you can find, right? And if you find malpractice, we as a community can just update this benchmark and get a more sophisticated result, more sophisticated performance overview. With this, let me quickly introduce the TabArena team. So this is a joint effort of many different institutes and many different people. Specifically, the first row you can see here, so Nick, myself, Andre, and David, which are the core maintainers of the current TabArena version, have put a lot of effort into making this a really great benchmark and also put a lot of discussions into this benchmark. So before I go into details what TabArena is, I would present shortly the background, because maybe you're not all on the same page. But very, very shortly, I'm talking about tabular data. Think of Excel sheets. So we have instances or samples and attributes/features, and we have a target feature somewhere that we want to predict. And in each cell, there's either a numerical value or categorical value. And we want to do predictive machine learning tasks, that is something like classification and regression, and maybe other things as well. And I hope this is quite obvious. Now let's talk about something that we need to make explicit. That is what we call independently and identically distributed data, so IID data. You can essentially see here a non-tabular example, but that I think is very easy to understand. We have two kinds of data, training and test data, and here the distributions are somewhat similar. And in train and test data, the distributions for non-IID data are not similar. And obviously in tabular data, it's not that trivial, not that simple that they are dissimilar or dissimilar. But generally speaking, in IID data, we assume that the training data is representative of our test data, and we can use, for example, random splits to evaluate them. Furthermore, one important background for this specific presentation, the AutoML seminar, is that there's a lot of relevance in our benchmark system to AutoML, because first of all, many successful AutoML systems focus specifically on IID tabular data, and they might not always say it, but they actually don't even support non-IID tabular data. Furthermore, as we shall show later, TabArena specifically enables AutoML to, for example, find the best models they should use in their AutoML system, simulate complex ensembling pipelines, even do meta-learning and portfolio learning, and specifically allow the transfer of academic work and models into usable industry pipelines. And this is really also one of the key motivations why Nick and I started this project to some extent, because we always needed to do benchmarking ourselves of these new models released in industry. And this is now essentially our way of making this a community thing that everyone can use the tools we are using. So TabArena is also a research platform for AutoML. With this said, let's look at what is TabArena version 0.1. Specifically, TabArena version 0.1 tries to do representative benchmarking, and therefore we need essentially representative models, datasets, and evaluations. And even more specifically, which is quite new in terms of benchmarking, is we need an explicit focus to represent, right? So otherwise we can't be representative for something. And I will now first talk about the focus, and then I will talk about the models, datasets, and evaluations. So what is the focus of TabArena version 0.1? And to basically give you the focus statement right away, we focus on tabular IID data spanning the small to medium data regime, so 500 to 250K samples in theory. We focus on predictive machine learning models for real-world classification and regression tasks, and we want to evaluate the peak performance of models. So these are the three key points that you need to keep in mind. And our goal was that once we had these points essentially settled in, we wanted to build a truly representative benchmark that can guide researchers and practitioners specifically for this focus. And to make it even more explicit, let me explain what we do not think is part of our focus, right? We do not think non-IID data is part of it. We also exclude future predictions, so that's the domain where large language models are quite powerful for tabular data. We do not care about tiny or very small data. We do not care about very large data. We also exclude tabular data with text or semantic context information. We also do not look at other tasks. And we, right, as mentioned, focus on peak performance. So trade-off in general, or Pareto front, is not what we are planning to evaluate. And essentially the statement is a very strong opinion that we just put out there. So let me maybe put that into context and explain to you why we think this is a valuable opinion. So first of all, why should we have a focus? Right? And the reason for this is simply that we want to make the implicit assumptions explicit. There has been a lot of research in the past that says, oh, I have the best state-of-the-art model for tabular data, but didn't say any of the, like say, important characteristics of what kind of data they actually work on. There's a bit of the saying, I know that I know nothing, because given our focus, I know that I know nothing about non-IID data. Furthermore, it allows us to have clear communication with practitioners and researchers. And that's quite important because every time you talk to practitioners, for example, on Kaggle or whatnot, they always sometimes claim, or on Twitter specifically, that our academic benchmarks are not representative of their real-world use cases. And that's usually the case because we never say what we are trying to represent. So if it doesn't work for them or it's not their data, then obviously it doesn't work. And furthermore, and most importantly, this specific focus allows us to clearly motivate which data and which models we want to include in our benchmark. So another important question is, why do we even care about machine learning on tabular IID data? This is like the most traditional task. It might be solved to some people, but it's still an omnipresent traditional machine learning task in industry and academia, and there are many problems in this domain that still need to be benchmarked, explored, and properly solved. Furthermore, this in general, right, tabular IID data is a really nice model development playground. So you can easily develop models in this playground without having a lot of hard assumptions or similar. And it's, as mentioned before, a key task for AutoML systems. And finally, it's just a stepping stone for exciting new avenues, right? Once your model actually works well for IID data, it's likely you can extend it to be context aware, you can extend it to be work for non-IID data. So these are things we also think are quite important. Why do we only focus on small to medium data, so 500 to 250K? First of all, simply because it's among the most common data types we have found and generally are used, but also because if you go to tiny data or to very large data, you have to completely change the pipelines of evaluations, of models, and of protocols you're using to even get good benchmarks. So this is a bit of a categorization of how can we still have comparable benchmarks in these different spheres. And finally, why do we focus on peak performance and not trade-offs? Well, because actually in most cases, we just want to know if a model is even good at all and if it would be worth it to make it better. Because a lot of times these new models that are being released, they come out in a state that can be still a lot optimized by just putting engineering into it. But we actually don't know if we should put the engineering into these models because we don't really trust most of the results in their papers. So that's one of the big reasons. Another reason is that there's the concept of if you want to optimize for trade-offs, you need to have user constraints, like what is the training time, what is the inference time I'm interested in. So that's a bit of a thing that also usually doesn't exist, that we would need to first find, and that's definitely future research. And then maybe finally, for the AutoML community, it might also not be that surprising that we think that the efficiency of the entire system, so the ensemble, is relevant and not the one of the individual model. And how you can get efficient ensembles is a completely different research direction. All right. With this focus in mind, let me talk about the models we are planning to use and we have been using. But first of all, maybe let me motivate why is it so hard to get these models right. Because there have been a lot of benchmarks that have been using models and, well, there might be some problems with that. So here, for example, is a search space of CutBoost that essentially is, given the description of the authors, a summarization of all prior workspaces. So a bit of like everything that was used in prior work and prior benchmarks has been summarized neatly to one search space. And I can almost guarantee you that if I would give this search space to a practitioner or to a CutBoost expert, they would be very confused about some of the parameters and might not think they are representative. Furthermore, what also always happens is that if you take a search space from somewhere else, it's not really aligned to your own pipeline, right? You don't really know if you should have added a parameter that really fits into your pipeline into the search space. And this is a bit of an implementation issue as well, because what we also notice a lot of times that there are models released that don't have a pip package, which is not too bad, but they often don't have their dependencies defined in a proper way. So they're really hard to use, and they're often from untested research code, so they're even further hard to use. And then at the same time, they have evaluated these models in very custom pipelines, probably sometimes never heard of scikit-learn, with also custom bugs, right? So there's a lot of work that this then, where you need to put a lot of effort into making this implementation actually be usable and be sufficient and be robust. At the same time, it's very understandable that academics and research code doesn't need to have such high standards. Moreover, it's very hard to know, okay, how to do certain model choices, because we don't have enough data or know-how for new models or even for old models documented anywhere. Finally, a big problem we notice in pipelines is that they have to some extent an ignorance of the target metric or user constraint. So if you optimize for a balanced metric, you need to make sure that your model is also knowing that it needs to be aware of class balance. And similar, if you have user constraints like time, your model also needs to respect these constraints. So in general, there were a lot of things you can improve in the implementation of models and their search spaces, and we tried essentially to do that. So what we essentially aimed for were these models, which consist of state-of-the-art tree-based models, neural networks, and foundation models. So specifically, the typical things like XGBoost, LightGBM, CatBoost, Random Forest. We have added as a new tree-based model experimental boosting machines, which is a very cool interpretable-based model. We have added MLPs from AutoGluon. We have added really these really new, really well-performing deep learning methods from recent work, and we have added the foundation models down here. And the important point is, besides just adding them, what we tried to do is we implemented them well and where possible with the authors. So really, we implemented their code, then asked the authors, is this okay for you? Do you have any comments? Do you want us to update it? And we did the same thing with the search spaces and even optimized the search spaces where the authors were not available, for example, or where it is like something like CatBoost, where we have a lot of prior knowledge and prior data from our own experiences and from AutoGluon, for example. And also note that, for example, for these two foundation models, the official papers and releases do not include a search space, so we didn't include a search space for them either. For Tabular, we have already added a search space now. So besides implementing all of these methods and getting them a good search space, we also need to make sure that we tune them in a sophisticated way. So that's, as you would expect for AutoML, quite important. And one of the key things we immediately noticed that is, well, we should use proper cross-validation because otherwise tuning will overfit, and in general you will overfit. And if you look at all the related work, if you see a 1 here, this essentially means that they used whole dot validation, and anything but a 1 is something like cross-validation. And you can see that most, and specifically famous prior benchmarks, did not even use inner cross-validation, which already makes it very questionable if their results are going to stay the same, or if there's something that, like specifically HBO, made them overfit. So besides that, we also added assembling. So this is specifically post-hoc assembling. So we essentially assemble all the configurations after tuning from one model. Right? So this is with this Caruana et al. Method, which is very powerful. And prior work looked generally at assembling, but usually not this kind of post-hoc assembling, but rather just like deep ensembles, these kinds of more simplistic assembling approaches. And as far as we know, post-hoc assembling is a very powerful tool that is very useful to get peak performance. And finally, we also did a lot of HBOs, a lot of tuning. We spent essentially, so we ran for each model 200 configurations, and each configuration had a time limit of 1 hour. So if you compare this to previous work, they also usually had a lot of HBO steps. Sometimes they had a time limit that was perhaps too small for large data sets, but in general, I think that has been working out quite well. And this now gives us essentially very powerful models that we hopefully then can use in benchmarking and in future work, and most importantly, also in practice. Now, given our focus on models, what data sets do we need to evaluate? And this is actually a pretty big topic because we spend a lot of time on these data sets, and this essentially is a summary of this. We did a lot of manual curation, and I will go through these different steps one by one in a second, but let's start at the start. So we had 1,053 data sets with unique names, so already filtered a little bit from 13 prior Tabular benchmarks, and we ended up with only 51. This is a large reduction, but we believe that every dataset we removed we should have removed them essentially. Right? So we even tried to get more datasets, but it was really hard. So let's move through this step by step. The first point is quite obvious. We just want to have unique datasets, right? You don't want to have the same dataset twice. And here we actually noticed that even though we filtered by essentially unique names, a lot of the times there were datasets with the same name, with the same dataset with a different name, or they were essentially the same dataset but with different preprocessing or different target features, and so on and so forth. And finding all of these duplicates was actually still quite a lot of manual work. Furthermore, we noticed the concept of similar tasks. So there were, for example, papers that released 5 datasets that all had the same features but different targets. And because of the overlap then, or creating a bias for this specific domain, we really thought, okay, we should just use one of these datasets. Another thing that was quite surprising to us are some of the duplicates were actually extremely not obvious. For example, there's the AutoML competition datasets, or many other competition datasets as well, where they just take a real-world dataset, rename it, and publish it. And then a lot of benchmarks in prior work used both versions, the original version and the renamed version, for benchmarking. And yeah, figuring that out requires a lot of detective work. The next step was that we only want to have tabular domain tasks. So we only want to have datasets that really represent tabular data problems as they are used right now. And as you see, essentially, we moved a lot of image datasets, while it's not necessarily means that you can't transform so what happened there essentially is that they transform image datasets into tables and then use the tabular model. Right? That is not a wrong thing to do, but in most of these cases, it was just very outdated and very wrong to do. For example, there were many datasets from the 80s where obviously something like pre-trained vision transformers didn't exist, but they then used tabular-based methods. But nowadays, this would likely, like a segmentation task, would likely just be solved with a segmentation model instead of a tabular model. So we removed most of them. We also removed, for example, forecasting tasks, and you can understandably solve forecasting tasks with normal tabular models, but at the same time, you would then need to compare to also forecasting models. And we also removed audio, text, and control/reinforcement learning tasks that are, in our opinion, not representative of the tabular domain anymore. And importantly, it was often very hard to figure out the original source of the data. We need to do really a lot of detective work to figure out what is the original paper and where was it uploaded and what is actually the data source. Another really important point was for us that it's a predictive or real predictive machine learning task, because there are essentially two concepts that are different. So there are many scientific discovery tasks, that's what at least I call them, in our field, where you essentially try to answer a why or how question. You can think of tasks where you want to do data analysis or figure out if there's a relationship between some features as such a scientific discovery task. And on the other hand, we have predictive tasks. For example, I want to train a model, deploy it in the web, and then run it on a server once I get new input data points. And the later case is what we're interested in, right? We really want to figure out what is a good model for these predictive tasks. So we removed anything we found to be a scientific discovery task. And usually you were able to make the distinction by just going to original paper and see how they use the data, or even sometimes they just explicitly said, this is not for predictive modeling, you shouldn't use it, but it still was used in many benchmarks before. And another really important point is that we want to have real-world data. So we removed specifically artificial and simulated data. We also remove deterministic data because we think that's not really a real machine learning task, because in most cases, this deterministic data is a function that you can look up on the web. For example, there's this heavily used tic-tac-toe data set, and if you just have the configuration or the features, essentially, you actually already know the solution given a deterministic function. There's nothing you actually need to generalize here. So we also removed all of these. And finally, we had essentially other reasons. Most of them were tiny data. And here it's important to note that, right, they were tiny data sets, so we just ruled them out immediately. But if we would have taken a closer look, many of these data sets would have also been removed for other reasons. Specifically, I'm not sure the exact number, but I think only 4 of these tiny data sets are older than 2010. So there's like a large number of them being from old educational resources where that was just the only computational feasible data they were able to use. We were also sadly had to remove a lot of data sets for quality issues. So there's, for example, data sets where they did wrong preprocessing and we couldn't reverse it, and then there was consistent data leakage, or there was target leakage that wasn't reversible, or a lot of times, not a lot of times, but a few times we actually just found data sets where there were absolutely no information where this data comes from, how it was published, what the source is, and so on and so forth. So we couldn't actually make a judgment call about if we should use this or not. And sadly, we had to remove 9 data sets that were pretty good for license reasons, mostly because of the Kaggle competition license, which forbids usage in basically anything outside of the competition. And finally, as mentioned, we focus on IAD data. So we removed any task that requires non-random splits during evaluation. So this means, for example, temporal-dependent features or group data. And for group data, you can think of algorithm selection tasks. And there were also many borderline cases, right, where you could frame this as an IAD problem if we remove a certain feature. So there were a lot of discussions about how we set this up and what counts as IAD and what doesn't count as IAD. So after this, we ended up with only 51 data sets. And the important point I would like to highlight is that these are very subjective opinions you are seeing right now, right? This is really what we think is a predictive machine learning task for tabular IAD data, and you might strongly disagree. And if you strongly disagree, please click on this link and comment on our curation data nodes. So essentially, for every data set we have looked at, we wrote down our nodes, why we removed it, and so on and so forth. And if you have a problem with any of the things we removed, please let us know. We would be happy in TabArena in the next version to include more data sets. All right, with this said, let me give you a short overview of what data sets we then have selected in the end. You will see on the task spectrum that we have a big bias towards binary tasks, and this is actually not something we were looking out for. It's just, let's say, a natural property of the distribution of public data sets. And this actually makes a lot of sense because if you're in practice, many times any task is transformed into a binary classification task because it's such a very interpretable and much easier to optimize for in, for example, KPIs. We have not really a lot of multi-class data sets and regression data sets, but that's something we are trying to target explicitly by finding new data sets in the future. Our licenses are also very good. They are public, as mentioned always, but they are still different. Our dataset sources are surprisingly a lot from UCI, which might some people think they're only old datasets there. That's not true anymore. They have actually updated their user interface, and there are a lot of very new, very good datasets on UCI, so their donation mechanism works really well, and they have a really good backup server. We have also a bunch of Kaggle and some from OpenML and some from other sources. And if you now look at the age distribution, which is also a really important topic in benchmarking, we actually have some new data sets, some semi-old data sets, and some older data sets. But I think generally speaking, we have a good distribution of age. If we now look at the number of features and number of samples, you can see that we actually are small to medium, really, right? We have from 1,000 to 100,000 roughly, and we have only at most, I think, 1,000 something features. So we don't have really large things. And again, we didn't filter a number of features, and we didn't filter, so we never had to remove a dataset because it was too large. Just didn't exist. It just didn't exist a dataset that was larger that fitted our criteria. And it's quite interesting because if you look at prior work and prior benchmarks, all the really big datasets turn out to be just vision datasets, right? If you have a dataset with 10,000 features, then it's very likely that this is a vision dataset from this work. Furthermore, a lot of large datasets that we removed are actually non-ID datasets, right? So if you look at TabRed or other benchmarks that are non-ID, you have very large datasets there, and that makes a lot of sense because if you have time resolutions, you can make your datasets very, very large. So to give you also a summary and comparison to prior work, we essentially also looked at all other benchmarks in our comparison and looked if they had any kind of curation or no curation. And then we essentially looked how many of their datasets, even if they had a lot of them, how many of them actually would have remained if they followed our criteria. And as you can see, it's a very drastic reduction of datasets for many benchmarks, and also for those that have like 300 datasets. All right. With this, let's look at how we evaluate our models on our datasets. And our evaluation design has roughly 3 major points. Starting with we repeat our experiments per dataset. So for small, we follow actually OpenML CTR23 a little bit. For small datasets with less than 2,500 samples, we repeat it 30 times because if it's small data, there's more noise. And for larger data, we repeat it only 9 times. And in any case, we use 3-fold stratified cross-validation for classification and for regression normal cross-validation, and repeat it either 3 times or 10 times. We use ELO as a rating system, so this follows other public leaderboards like Chatbot Arena and whatnot. The criticism of ELO would be that it's a pairwise model comparison and that it's absolute, so that is something that is a fair criticism. We also compute other metrics you can look at. But the important point for us is that essentially, for example, a 400-point ELO gap corresponds to a 91% win rate, and this shows a consistent improvement, right? And that's something we are very interested in because if you have 2 models and one is consistently better, or you could also say significantly better than another model, then this shows that there's some fundamental difference between these models that is worthwhile investigating from our side. And we can figure out if it's worth it to do the trade-offs at a later stage. We also use robust metrics appropriate for benchmarking, for binary, multi-class, and regression, different metrics, very much following the AutoML benchmark. I think besides log loss, these are very good metrics, and log loss can be disputable. But for example, something like accuracy wouldn't be an appropriate metric for benchmarking just because we, for example, do not have the cost metrics associated to the different classes. But this is also a very long discussion. I'm happy to have that offline, but we just stuck to what we think is good. A new thing we introduced is what we call a reference pipeline, because something we noticed in prior benchmarks is that essentially you have all of these models on your leaderboard, and practitioners can, first of all, not run these models because they're in complicated benchmarking code. And second of all, they don't actually know how their model or their pipeline corresponds to this leaderboard or where it places on this leaderboard. So what we then do is essentially we think, okay, we need to see some pipeline that people can run easily, and that then they can compare with their own results how it compares to this leaderboard. And something good that exists for this is AutoML, of course. So we use AutoGluon on train for 4 hours as a reference point and always include it in our results. And finally, we actually do store and share extensive metadata. So as part of the evaluation, we store something such as validation predictions, test predictions, training time, inference time, pre-computed results, and hyperparameters. And this is really what I meant with this is a playground for model development and a playground for AutoML system development, because this is essentially TAB Repo 2.0. This is how this entire project started. And we have everything we need to really make AutoML systems really, really great. All right, to also compare our evaluation design a bit to prior work, as mentioned before, we have the inner split, which has a big factor on representativeness of the benchmark. We have our outer splits, where we also have a large number or a good number compared to prior work in our mind. And we have this column with results available. So there are benchmarks that don't share any results. There are benchmarks that just share the pre-computed results, and we share the predictions and everything else. So it's really about being able to compute your own metrics or simulate stuff on top of these predictions. All right, with all of these things out of the way, we can finally talk about the results, the one thing everyone cares about, benchmarking. But before I can do that, I need to give you a non-neutrality statement or competing interest statements, because this is a benchmark developed by people that have been developing methods that then are part of this benchmark. Specifically, right, we have essentially our own horse in the race, and therefore you should assume some bias. We obviously didn't, we tried to remove every bias and we tried to make everything as fair as possible, but you should be aware of this. And furthermore, we would be extremely happy if you could find any problems or biases in our benchmark, because then we can just update it and it's better. So that's really the spirit of the living benchmark. So if you're annoyed by this, please look at my benchmark and make it, or show me the mistakes in it. All right, the main leaderboard, the main results is the following plot. You can see on the y-axis the ELO, you can see AutoGluon as a reference pipeline up here, and then you can see the different models in their default state, in their tune state, and in their tune plus ensemble state. So important, this is assembling just over the same configurations of the same model type. Right, so for example, this green bar represents what happens if you tune and then ensemble just real MLP. And you essentially can take a look at this for a second. It's a lot, but we see very different distributions over these different modis of default, tuned, and tune plus ensembled. And the two things I would like to highlight is first, that you can see cut boost is the best by default. And under the tuned regime, it's also still the best by peak performance measures. But it doesn't gain a lot from assembling. So if we now look at the deep learning methods over here that really gain a lot from assembling, they really start to dominate and have really great performance. And as mentioned, if you do tuning, this assembling has a really small cost in offline time, and in inference time, it's also manageable. And there's research to make it even faster. So this is really a first great look at how these models compare, and also to note, right, this observation that cut boost dominates and is the best in the default regime and the tuned regime is very much aligned with prior work. But this tune plus assembled is something we really put a lot of effort in, which is something prior work has so far not looked at a lot. As you can see, we only show TabTBT as the only foundation model in this plot, and it's somewhere in the midfield. And this is because the other foundation models actually cannot run on all datasets. So we also compare them on their subsets, as you can see on the left for TabPFN, which is less than 10,000 training samples, or less equal to than 10,000, and 500 features. And for Tabular on the right, you can see 100,000 training samples, only classification. And now we can essentially take a look at this for a second. The most important observation is, and that you would also have expected, is that by default, as you can see here and over here for Tabular, these tabular foundation models really dominate. So they are really strong, out-of-the-box, in-context learning models. You can also observe that if you start tuning and tuning assembling, other models can really start closing this gap to the default configuration. But then if you start to tune, for example, TabPFN, similar to the tuning in the Nature paper, and assemble them, you get even much, much better performance, outperforming AutoGluon, quite largely. And also please note that over here for Tabular, we do not have HPO results because there was no official search space, but we already have this essentially fixed. In the next version, there will be a search space. It's already on GitHub. If you're interested, look at our GitHub repository. All right. As mentioned, we are interested in peak performance, but there's also something we can consider, that's efficiency under peak performance. So how expensive is it to actually get to the peak performance given the implementations we currently use? And an important note I would like to start with is that we look at train plus validation time. And this is really a critical thing to do. This is a must. A lot of prior workers only looked at train time and then said, well, I can train a foundation model in 1 second, and therefore it's really good. But in reality, for example, let's look at TabDPT, which also can train in a second. What you need to be aware of is that you have to always cross-validate these models in reality, right? Before you can deploy it on any new data set, you need to know if it actually fulfills certain constraints and characteristics, like an accuracy minimum on this new data set, or if it has some other problems, right? The model verification pipeline needs cross-validation. And TabDPT is a method that uses retrieval at inference. So it actually is a foundation model that has very quick fitting, as always, but does 1 forward pass per sample. So if you have a large data set and you do cross-validation, this is extremely expensive. As you can essentially see here. And extremely is also relatively, right, compared to other methods that you can see here, but still something to be aware of. So we essentially show you the time it takes to cross-validate and fit the final model of any of these models. And the second observation you should be able to see is that these green squares are usually much more expensive. So assembling is, as you expect, inefficient, also doing inference, but maybe not that much for some cases, like here or here. But as mentioned before, it might be very much worth it for you. Lastly, finally, you can see that deep learning models are more expensive because all of them are down here. So most of them are down here. So really, this kind of deep learning approaches, as we've seen in the past, as we already technically know, that they're just usually more expensive in training. But we believe this is also another part of why CutBoost is so good. It's just a matter of good implementations, right? Some of these methods are very new. Their implementations have a lot of engineering potential, right? If we would re-implement all of them in Rust, I think this plot would look very different. And CutBoost just had a lot of time to optimize their implementation. All right. Another result we were able to figure out, and which is very important to communicate always, is essentially that you hold holdout. So you should not use holdout validation if you do benchmarking for this kind of data. And what you can see essentially here is the performance of Tune plus Ensemble, so the peak performance, using holdout inner validation or using inner cross validation as our default paradigm. And what you can observe immediately that you have a much worse peak performance. For real MLP, it's actually almost 400 ELO, so that's a massive gap. You see that the relative model ranking changes, right? Here LightGABM is best, here real MLP is best. In general, it just looks very different. And more importantly, if you use something like holdout validation doing your benchmarking setup, you should be careful with post-hoc analysis because they might be very much unreliable, right? If you didn't really get the peak performance for a data set, then the analysis you can do on meta features or any other characteristic is likely also flawed. And the thing that I would like to highlight on this page as well is that all of these holdout results are simulated, right? As mentioned, we store a lot of results and we can essentially just run our normal pipeline and then afterwards, post-hoc, just compute what would have been the holdout validation score, or what would have been the score if we use 4 folds of 8-fold cross-validation instead of 8. And then you can really find some optimal performance trade-off. Next up, something that should be quite obvious also to a lot of AutoML folks is that assembling is really, really powerful, right? So here we essentially show that model-agnostic assembling, so if you do not assemble just for the real MLP models, but you assemble for all models in this pipeline, gives you a much more significant performance boost. And importantly, this is essentially like a simulated AutoML system now, right? We have all of these results saved. We can just simulate how good an ensemble of these models would have been. And again, as mentioned, this is just 4 hours, so that's also comparable to the autogluon time we took here. It's significantly better, and there's still a lot you can do here because this was a very naive assembling approach, essentially. And this is also something we would like to highlight critically, that a lot of the prior benchmarks in tabular data have focused really on this kind of research goal. I want to show that tree-based methods are better than deep learning, or I want to show that deep learning is better than tree-based methods. And while this was a really good driving factor for our community, it's just really framing. There's no substance to it in reality, at least in my opinion, maybe some of my co-authors as well, because the real research goal is what model will give us a better final performance in the final ensemble, right? This is really a big question, and how we can even research this is also a big question, and we hope that TabArena helps with that. But in general, we are still interested in finding the best models, right? So that's really cool. Now, to conclude a little bit, these were the results. But besides just giving you a nice leaderboard and some insights, what TabArena is really about is its ecosystem, right? We have produced TabArena to be used specifically also by us and others to have benchmarking efforts made easy or to produce future cool work for our community. And the first thing we have introduced is a Hugging Face leaderboard, or actually a collection of leaderboards, you could say, because the goal of this place is really to have at some point a leaderboard for every potential use case and domain of tabular data you're interested in. That's a long-term vision, many years in the future. But right now we start essentially with our current results, and we already updated this once, and it will be updated again soon with many new results. At the same time, we have started to take our first steps at the living benchmark. We have added new models like TabFlex and Beta TabPFN. We have added or started to improve existing models with the authors like EBM, and we are starting to add new models as well. And then we will benchmark them and put them on a leaderboard, and we can figure out if they would actually be useful for an ensemble. Moreover, as mentioned before, our goal was to make all of these models essentially industry ready, right? And this is something we also made progress towards, because all of the models we have implemented can be used in AutoGluon-like fashion, essentially, right? So here's an example of using RealMLP on a binary classification data set, and it's just calling the model, you can run it, and it fits, right? This is really nice. We have many more examples under this link, specifically also for using them as part of AutoGluon or more complex tuning plus assembling pipelines. So please check them out if you want to use any of them. And also, right, this is, as mentioned, there are AutoGluon developers working on this. So the next version of AutoGluon will very likely include some of these models. And as a result, we already know it's going to be much, much better. Finally, as mentioned before, we have this public dataset creation. We have a lot of comments on our datasets. And please, if you have any complaints or want to add new datasets, go to this sheet, add a comment. We have already some candidates for new datasets. This is just the next effort, a new benchmarking effort needs to do this. And finally, we also want to support cheaper evaluation for papers, right? Running all our experiments is very expensive. So we introduced TabArena-Lite, and this is essentially the official TabArena suggestion for using it in a paper. So this is essentially just running the first repeat or per dataset. So you still do all inner repeats, but only the first repeat per dataset. So it's not very representative. But if you're good on this or competitive on this, this is enough signal for us to especially include your model and for us to run the large benchmark for you, for example. And as mentioned, this is written down there, it's 16 times fewer jobs, so it's actually much affordable. And if we reduce the number of configurations, you can really quickly benchmark some of your ideas. And I think, for example, I benchmarked TabFlex, which is a very fast foundation model, but that took, I think, maybe 20 minutes or something like this. All right, with this said, this is a bit of the ecosystem we are maintaining. What is the future of TabArena? What is version 1.0 going to be? And well, hopefully it's going to be something far in the future because it's a lot of work. Specifically, we have two main concerns, that is datasets and benchmarking. So in terms of datasets, we need to somehow get better licenses and data platforms, because while we have really great data platforms, there are still too many problems for us to really have a native platform where we can share data and where we have good incentives for other people to share their data and that we then can use them for benchmarking. Moreover, we need much more data diversity, we need more domains, we need tiny data, we need large data, we need non-ID data, we need tabular data with text, with images, and so on and so forth. So these are essentially all new projects that can be done as part of TabArena. Another really important point is that we essentially took the data sets as they were pre-processed originally. So we took the most raw state we were able to find. But we know for a fact that if you do pre-processing or feature engineering, you can, like, the model ranking likely changes, right? So this is another really big problem. How can we evaluate data sets with expert feature engineering for specific models? That's something we also want to look into. On the benchmarking side, we have overfitting the benchmark as a big fear that people always bring up. My opinion is that it's actually a completely trivial problem. There are also papers for ImageNet and co. saying it's not really a problem, but it's a different discussion. At the same time, we have immense bias from data contamination, and it will only get more, right? We have pre-training of foundation models that probably have seen some of our datasets or will now start to pre-train on our datasets. And we have large language models that for sure know our datasets because they know the entire internet. And finally, another really big constraint for benchmarking to make it truly representative for realism and for deployment is that we need to somehow find user constraints and metrics that align with their goals for each data set, right? We really need to know for each data set what would have been the KPI, what would have been the thing you really want to optimize for, and just deciding or coming up with such things is really hard and will take a lot of time. So to summarize the entire talk and to give you some takeaways before we go into the discussion and questions, you should love benchmarking because TabArena is now a truly representative benchmark for machine learning on small to medium-sized IID tabular data, so that's great. You should now know what SOTA is for our focus, and you should know that you get it with ensembling, right? CatBoost can shine and is really great. Deep learning with ensembling also dominates, and there's a promising future, if not already, we are in the future of foundation models. And finally, it's a living benchmark baby. That's our internal motto, essentially. We will update TabArena. We already have updated it a few times, and we will do much bigger projects in the future for more data, models, and tasks. And with this, thank you very much, and I'm happy to answer any questions or have a lively discussion.